Hello, this is Jack Jackson with Part 5A of our series of lectures on continuous distributions, and the first one on normal distributions. Normal distributions are extremely important. In fact, normal distributions form a family of distributions which are the most important distribution family that we can look at, more important than any discrete or any other continuous distribution. It is a continuous distribution, and why is it important? Well, there's a couple answers to that. One answer is that it's useful for modeling many real-world data sets. For example, heights. And we'll see when we look at the graph of the normal distribution, it's a bell-shaped curve. Let's kind of go ahead and look ahead. So it's going to look something like this. And notice that it has a lot of probability near the middle, and it trails off on both ends. And a lot of things in the real world are distributed like this. For example, heights, there's a lot that are near the average and a lot less when you go really extreme. So lots of people near average height, but very few people over 7 feet tall, and very few people, adults anyway, under 4 feet tall. So if you're very far off of the mean, there's less and less probability of that happening, with a big chance of happening right in the middle. Many other things follow that same kind of shape as well. Weights have a tendency to come that way. A lot of times weights of animals, people, whatever. Intelligence can be measured on, like IQ is measured on a scale that has that kind of distribution. Lifespans have a tendency to be that way. A lot of people have near the average length of lifespan, a few very, very short, a few very long, a lot near the average. Some measures of manufactured items also fall in this category. For example, let's suppose we're making ball bearings, and the diameter of the ball bearings we make most of them will be pretty close to the average, but there may be a few that are on the extremes, extremely high or extremely low. But they will generally have a tendency to be modeled quite well with a normal distribution. Exam scores happen to be this way, not so much for a particular class, but if you have large-scale exams like the ACT exam or the SAT or some large exam like that, they have a tendency to follow something like a normal distribution, and there's lots more. So those are just some examples of real-world data sets that follow a normal distribution, or at least can be approximated quite well with one. But we also have something we're going to talk about in a later video that is called the central limit theorem. And it says the distribution of sample means approaches a normal distribution as the sample size increases. And it's because of this fact that is so important that we can make inferential statistics work. And the whole goal of this course really is to get to where we can understand and use some inferential statistics. And we need to do this background material so we can get there. And the key to making all of it work really is the central limit theorem. And this says that this normal is sort of our idealized distribution as the sample size gets bigger, at least for the distribution of sample means. And so that's going to be extremely important for us later on. So because of these two things, because of the central limit theorem, and because they model real-world data so well, normal distributions are the most important distribution we're going to look at. We're going to start by looking at what's called the standard normal distribution. It has we're going to see here in just a few minutes that it has a mean of 0 and a standard deviation of 1. And has a PDF formula here given by this formula here, 1 over the square root of 2 pi times e to the negative x squared over 2. Now this is actually quite an amazing formula if you think about it. It's got a lot of the most important numbers in mathematics right here in the formula. It's got the number 1, essentially the number negative 1, the number 2, it's got a power 2, it's got a square root, it's got the number pi, and the number e. All those are very important numbers in mathematics, and they all show up in this one formula. It's kind of interesting. In fact, it's one of the things that we know, if this is going to be a probability distribution, what are our two conditions? Okay, remember the two conditions are all the y values have to be positive, and of course e to any power is positive, this coefficient out here is positive, and so the whole values are all positive. In fact, they never actually become 0. In a distribution, it could be 0 or positive, but never negative. This one's only positive, and it does have asymptotes going out towards 0 on both ends. So the bigger you let x get, or the bigger the absolute value of x is, the closer you get to 0 going to the far right or out to the far left, either one. And it's really an amazing fact that this 1 over square root of 2 pi is got to be the exact number there to put so that whenever you graph this, you're going to get a total area under this of 1. We're going to investigate that a little bit as we go through this lecture. Convince ourselves that that total area really is 1. But anyway, this is the formula for a standard normal distribution. Let's look at some characteristics that the graph has. Well, this has a shape that we often call a bell-shaped curve. So sometimes when you hear people talk about a bell-shaped curve, they're talking about a normal distribution. And notice it is symmetric. We'll look at that some more in the next slide. But it's symmetric about 0. And the highest point is right there on the y-axis. So that's going to tell us that the mean, median, and mode are all 0. And this particular one has a standard deviation of 1, which we'll see a little bit later on. So one of the characteristics that we need to notice here is that if you take this formula and you replace x by minus x, once you square it, you get the same thing. Whether x is 4 or negative 4, you get the same output. Whether x is 5 or negative 5, same output. 3 or negative 3, same output. So when you put the opposite of x in here, you get the same y. So that says if we pick a particular x, 1 here, we go up a certain height, negative 1s go up the same height, which means this is symmetric about the y-axis. Well, that means it has no skewness whatsoever. Remember, a skewness of 0 means it's absolutely perfectly symmetric. A skewness that's positive would indicate that we have a longer tail on the right than we do on the left, and skewed negatively or skewed to the left would say that we have a longer tail on the left. In this case, we don't have either one of those things. We have exactly the same amount of tail on both sides. It's symmetric. And so anytime you have it symmetric about the mean, you're going to get a skewness of 0. And we can also see that the highest value you're going to get here is when x is 0. And let's see, 0, square root of 0 divided by 2 is 0. The opposite of 0, either 0 is 1. And so if you plug in x is 0, you're going to get 1 over the square root of 2 pi. And so the height here is 1 over square root of 2 pi, which is around 0.4. Not exactly 0.4, but somewhere in that ballpark. And so this is not very tall, of course. As you know, all of these distributions, the total area has to be 1, so none of them get very tall. So we're pretty close down here. And this one, most of the real action you can see happening between negative 4 and 4. Out beyond 4 and negative 4 to the left and positive 4 to the right, out beyond that is just so close to the x-axis that there's very little area out there for us to consider. Most of the interesting stuff is happening right in here near the x-axis. Okay? Now, because of the symmetry, that means you're going to have exactly half the area to the left of 0. So the shaded area you see here, which represents the probability that x is less than 0, is 1/2. And of course that means the unshaded area here under the curve on the right side, the probability that x is greater than 0, well, that's also 1/2. Well, that makes 0 the median. Remember, in general, the median is the x value, so that the area under the curve to the left is 1/2 or 0.5 or 50%. So there's a 50% chance that you'll be below 0 when you're selecting something from this particular distribution. We'll show later that the standard deviation is 1. But, of course, because of both the symmetry, well, basically because of the symmetry, then that point where you have the symmetry, in this case 0, has to be the mean, because it's got to be the balance point. Well, if it's perfectly symmetric, you can easily see that that mean is going to be 0. And, of course, it's also the mode, because as I plugged in the x is 0, we got 1 over square root of 2 pi. And if you plug in anything bigger, then this value here, e to the negative x squared over 2, for any value of x is going to be a number less than 1. And so when you multiply that by this number 1 over square root of 2 pi, you're going to get a smaller number than 1 over square root of 2 pi. And you see that actually the further you get away from 0, the smaller number you get. And so we see that the mode then will be at 0 because that's the highest point. So on this distribution, the mean, the median, and the mode are all the same. The mode is the high x value that gives you the highest value on the curve. The median is the x value so that the probability to the left of that x is less than that, is 1/2. And the mean is the balance point, or the expected value of x. And they're all three the same thing. So in this particular case, because of this high degree of symmetry, we have the mean, median, and mode. All three measures of central tendency are the same, and in this case they're 0. Now, one of the things that we want to know is that the total area is 1. Now, so far you've just sort of been trusting me that that's the case. If it is the case, then this area here would be a half that's shaded. Now, how can we maybe verify that? Well, turns out that's very difficult to show analytically. It's possible to do it, but it's a pretty hefty project for a Calculus 3 class, so certainly not something we're going to do in our basic probability statistics class. But we can kind of convince ourselves with this numerically. So we can use the TI-84 calculator, remember, to find areas under the PDF curves, between the PDF curve and the x-axis, between some numbers a and b, by using the area calculator, also known as FNINT, function integrate, numerical integration, or area calculator on the calculator. And if you watched the last video, you know how to do that. Okay, and so let's use that command and see if we can do some of these areas. So let's start by finding the area under the curve between -1 and 1 and see what we get for that. Here's kind of the syntax for the TI-84 right here, using the older notation. If you've got the pretty print notation, it's going to look more like this right here on your newer operating system on the 84. In the older operating system, it looks something like this. So with this case, A is -1 and B is +1. So go ahead and work that out for this first line, for -1 to 1. Try to do that now on your calculator. It's good for you to practice this function integrate thing. By the way, remember function integrate is Math 9. Okay? Stop and do that now. Press pause. Well, what we should have seen on the TI-84 is a series of screens that look something like this. So if you didn't get this done before, have your TI-84 out, and or your other calculator if you have some other calculator, and see if you can make it do what we're doing here. So I did it two different ways. One way is I did it by the graphing window. So I put in y1 equals our function right here, 1 over square root parentheses 2 pi close parentheses times e to the power, and that'll open parentheses, -1, not minus, but not subtract, but -1 times x squared divided by 2, close parentheses. Notice I had to put the power in parentheses, and I got to have parentheses around the 2 pi. Now we got to find an appropriate window, and what we were looking at in the last window, 0 to about 0.4 is going to work. I went just a little bit beyond that. I want to have some room at the bottom of the screen to show some calculations. So I went down to -0.1. Not because the graph goes down there, but I don't want my calculations I see here later on to show up on top of my graph. And then I went up to just beyond 0.4. I went to 0.41. And for this particular exercise, because my table eventually goes down from -7 to 7, I'm going to set my x min at -7 and x max at 7, and I'll have to just mark off at once. Then we want to calculate, so we can graph it, and there's a look at the graph. Now we want to calculate the area. So that's calculate that second trace, and then number 7. Okay, and there's that funny looking S for sum, and we're summing up areas, summing up probability densities. Okay, also known as a numerical integral. So press number 7. It's asking you for a lower limit. We type in -1, enter. Asks us for an upper limit, 1, enter. And then it might take it just a second or two to do this, but it will shade this area, and that's the area between -1 and 1 that's underneath the PDF curve and of course above the x-axis, and that area turns out to be about 0.6826849. Now if we don't want to see it drawn, we can do it on the calculator. By the way, I went ahead and hit clear draw and enter to erase this, so the next time when I do it, it doesn't already have something shaded. But to do this directly on the home screen, I say function integrate parentheses. Now if I've already got my formula in y1, I can put that right here. If I don't have it in y1, whatever I've got typed right here, put that in place of the y1 here, and that'll still work. Then it's always comma, x is the second part, comma, and then our a and our b, so -1 to 1. And here, this actually picks up a couple of extra digits, 682688949, and then after that it's a 2 and a 1. So approximately 68%. So notice that the majority of the area right here that's shaded, that's 68% of the area that's within one standard deviation of the mean, from one standard deviation below to one standard deviation above, or on the standard normal from -1 to 1. And that turns out to be the majority of the area, over half. Actually, it's about 68%. So we can put that in our calculator in decimal form and then round it off in percent form there. Okay, now that you've seen that, I think you should be able to do the rest of these. Let's go ahead and do them one at a time, though. Go ahead and figure out the probability that x will be between -2 and 2. We'll look at that. Shade that area on your calculator. Also grid it from the home screen. Press pause and do that now. Well, notice this time we got from, this is the shaded area here that's within 2 standard deviations of the mean, from -2 right here to +2 on that, and we shade under the curve, and that turns out to be over 95%, about 95.4% of the area that's within 2 standard deviations of the mean. So you only have to go out 2 standard deviations. Now remember, Chebyshev's theorem said, well, and within 2 standard deviations we've got to have 3/4 of the area. But in fact, for a normal, we get much higher than that. We get actually 95%. So we can add that to our table. Alright, go ahead and do the next one, -3 to 3. Calculate that. Press pause and come back when you're ready. Okay, well, you're back now. You should have gotten this. Let's see, about 99.7% of the area. And so here it is, the final shaded version. This is actually shading from right here at -3 to here, which is +3. It doesn't have anything shaded beyond that. And that turns out to be, well, almost all the area. It's 99.7% of the area, over 99.7% of the area, is within 3 standard deviations of the mean. So once you go 3 standard deviations below up to 3 standard deviations above the mean, you get by far the bulk of the area. Notice we're getting close to 1 already. Not quite all the way, though. Let's keep going. Okay, what about from -4 to 4? Go ahead and do that one now. Press pause. Okay, if you check this one, you see that now we're up to 99.993% of the area. Go ahead and do these next ones. How about -5 to 5? Press pause and then come back for that one after you've done it. Okay, now that you're back, look at this. Now it's 99.99994% of the area. I mean, it's practically all of it. We go a little bit more. How about the 6, from -6 to 6? Check that one on your calculator and then come back. Okay, you're back. Well, look at that. That's just 0.999999998. Very close to 1. From 6 standard deviations below to 6 standard deviations above. As far as this one rounds it off here to fewer decimal places, and on this screen it actually says it's 1. Of course, it's a little bit less, but it's way out here in the digits where it's less. So it's always pointing to a bunch of 9s and then something smaller out here. And finally, let's do one more from -7 to 7. And if you do this one, you'll see that not only on this screen, but this one over here, as far as your calculator can tell, that is 1. Of course, it's not really. It's a whole bunch of 9s. I don't know how many. And then probably something smaller than 9. But the point is that it's so close to 9, so close to all 9s, so close to 1, that your calculator can't really tell it apart. So we've actually gone to the limits of our calculator and showed that it looks like this is going to be 1. Now, this is not a formal analytical proof, but I think we're pretty convinced now at this point that this area really is 1, and this 1 over square root of 2 pi is the right thing that needs to be in the formula, so it does work out to be 1 for an area. Kind of amazing result. So notice, within 1 standard deviation we have 68%, within 2, 95%, within 3, 99.7%, and by the time we go out 4 standard deviations, it's closer than 99.9994%. Okay? So you can see here, again, if we divide this up here into pieces, here's the standard normal curve again. Mean is 0 right here. Here's 1 standard deviation at 1. 2 is 2 standard deviations, 3, 4, 1 below, 2 below, 3 below, 4 below. And so this region here from 0 up to 1 and under here, that's going to be 34%. Another 34% is right here between -1 and 1 for a total of 68% roughly between -1 and 1. So between these two purple lines and up to the curve on the blue curve on the top and the x-axis on the bottom, this total area here is 68%, split evenly into 34 and 34%. Okay? Now, if we go out, so notice that you've gotten most of the area really close to the mean. So if we go out another standard deviation, we're adding the same amount of x value here on both sides that we already had. We're doubling our width, but we're only picking up another 13.6% right here between 1 and 2, between 1 standard deviation above the mean and 2 above the mean, and 1 standard deviation below the mean and 2 standard deviations below the mean. That picks up another 13.6% there as well. In other words, we're adding 27.2%, which brings our total from x minus 2 sigma to x plus mu minus 2 sigma to mu plus 2 sigma to be a total of 95%. So between these lines here, we get a total of 95% roughly, a little over 95% really, about 95.4%. Now, as we go on out a little bit more, we're going to pick up even less. So between 0 and 1, 34%. Between 1 and 2, 13.6%. Between 2 and 3, only 2.1%. In the same way, it's symmetric, so 2.1% over here. So if we put all this together, the 2.1% and this one, and both of these 13.6% and both these 34%, we add all that together, we get the area from mu minus 3 sigma to mu plus 3 sigma. We're at 99.7%. Now, some books will talk about this as the empirical rule, saying when we have a normal distribution, these are same things that you might memorize. If you remember, Chebyshev's theorem also said something about this. It said that within 1 standard deviation of the mean, well, we didn't know anything about what might be within there. But we did know that within 2 standard deviations of the mean, we ended up with, well, it was 3/4 of the data. And within 3 standard deviations, we got 8/9 of it. Okay, about 88%, 89%. So notice that this is much higher than that. We know for sure we get 68% within 1 standard deviation of the mean and 95%, much higher than 3/4, within 2 standard deviations. And within 3 standard deviations, a lot more than 88, 89%, but actually, well, 99.7%. So if you know your distributions from a normal distribution, then you know these percentages. Sometimes the book will talk about the empirical rule, and what they're talking about there is a distribution that is basically assumed to be normal or very close to the normal. So if you got a mound-shaped data here that's symmetric about the mean, then kind of humped up in the middle there and then down on both sides, particularly if it's symmetric, then we should expect numbers closer to these guys here. Now, what happens if we replace the formula? Before we just had an x here. What if we replace the x by x minus mu? How is that going to affect us on the graph? Let's take a look here at this particular sketchpad sketch. I have, well, almost a standard normal here. I've got 1.01 instead of 1 on the standard deviation. That's as close as I can get it with these sliders. And here I'm going to change the mean by doing this. What happens if I increase that mean? Look what that does to the graph. It's staying exactly the same shape, but it's just shifting it to the left or to the right. So, for example, here's a mean of 0.5. Okay, and so that says right here at 0.5, that's the mean, the median, and the mode is now 0.5. So in general, we know from our algebra classes that if we replace x by x minus a, it's going to shift the graph horizontally by a units. Okay, and that's no exception here. We can see that it's just simply moving this. So the mean measures what the mean's supposed to measure. That is the center of the distribution. So, changing mu shifts the graph horizontally, changing the center of the graph. So in this particular graph down here, this was made in Graphmatica, the one in the red is the standard normal, a mean of 0 and a standard deviation of 1. All these have the same standard deviation, so I left the sigma as 1, so we're just using this formula here. Notice there's no sigma in it, the 1 just kind of cancels out. But we're putting different values for mu. Here's the mean of 1, is this one right here, kind of aqua color. This purple one's a mean of 2. This one here, I guess it's a maroon maybe. That's a mean of 3. And there's a green one here, a mean of -1. An olive one, mean of -2. And a blue one here, which has a mean of -3. Now I keep saying this mu is the mean. How do we know that it's the mean? Well, we also know it's the mean because of the symmetry that we looked at before. And of course when we shift it by putting in a new value for mu, we're just shifting that line of symmetry. But we should also be able to figure this out using our calculator. For example, remember that the mean is the expected value of x. So that should be able to, at least approximately, we should get it by our numerical integral or our area calculator. And what do? We do x, that's summing up the probabilities of x times the PDF, comma x, comma, well, this should be minus infinity and infinity. And it turns out if we'll go 10 standard deviations below and above the mean, that's going to be close enough that we're going to get what we want out of this. Remember, actually, if we went 7 standard deviations above and below the mean, that was enough that our calculator really couldn't tell that there was any area outside of that. So certainly if we go 10 above and below, 10 standard deviations above and below the mean, at least for a normal distribution, that's a reasonable approximation of negative infinity for mean minus 10 sigma, and then mean plus 10 sigma is a reasonable approximation for positive infinity for what we need for what we're doing. So what we're going to do is I'm going to put 2 and store it as m in my calculator. So right now the m is going to be the mean, and I put in this formula right here. Function integrate, that's math 9. X times parentheses 1 divided by square root of 2 pi, 2 pi's in parentheses. Now close the fraction there. That puts a parentheses around that fraction. Then it's times e to the power, parentheses, -1 times parentheses x minus m, close parentheses, square, divided by 2, close parentheses. And so that gets us this. So that's x times the PDF. Then it's comma x, comma, and we want minus infinity, infinity. Well, we're going to use m minus 10 and m plus 10. Close, and hit enter, and notice I got m back again. Well, if I change m to 4, I could now say 4 store m and hit enter, and then do second enter a couple of times till I get this expression back again and hit enter again. This time I get 4. And I can do this over and over again. No matter what number I put in for m, this is always going to output the same number m. So this tells us that, sure enough, m in this formula really is mu, so it is appropriate to use the letter mu there instead of m. Let's do the same thing for the standard deviation. Remember the the variance actually. The variance, sigma square, is the expected value of x minus mu square. So remember that would be sum up, function integrate, x minus mu, the mean, which is m, square, and then we put in this formula here for the PDF. Now this is the general formula for the PDF that has m and s both in it, with respect to x, and we go from minus infinity to infinity, and this time again I'm going to use m minus 10 times sigma and m plus 10 times sigma. And if you do this, we get s squared. So we see that s squared is really sigma squared is the variance, and of course the square root of that would be the standard deviation. So the s here really is sigma, the standard deviation. We can see that on our calculator. So I don't know what I have stored as m, but whatever I've got stored as m, that's fine. And then I take 5 stored as s, and then I do this thing, and I should end up getting 5 squared, which I did. I got 25, and you can see the syntax here. It may take you a minute to go through all this. It's a lot of stuff to type in, but it's the same as this up here. To do this one, I don't have to type it again. I can store something else as s. I stored 4 as s, and then did sec enter to get 4, and then I did second enter a couple of times until I got this formula back and hit enter one more time, and this time I got 16. So notice in both cases, I got the square of whatever s was. So that's only 2 examples, but you could do this for many examples, and they would all turn out to be the same. You'd always get the square of whatever you started with for s up here. So that shows that the output is s squared. Okay? And so s is actually sigma, the standard deviation. So that leads us to this general formula, that f of x is 1 over sigma times the square root of 2 pi times e to the power negative x minus mu in parentheses squared divided by 2 sigma squared. Now what's that going to do to the graph as we change the value of sigma but leave mu fixed? So for example, if we leave mu fixed at 1, what's going to happen as we change sigma? Let's take a look back at our sketchpad sketch and see what happens. Okay, well I'll leave the mean to be 0.5 here. So we leave that alone, and look what happens. As we increase sigma, look what happens. Well, you can see it. You can see it here. It's this distance of this part right here is actually sigma. And the bigger sigma is, look what happens. It's getting shorter and fatter, more variable. It's less humped up around the mean. Okay? And sigma can't get 0. It's got to be positive. But notice if you get a small sigma, you have lots more area really close to the mean. So it is less variable, more consistent, smaller variability. Now, this is exactly how we interpreted sigma earlier in the course. Is a small sigma means your data is very closely packed in near the mean, whereas a larger sigma means it's spread out further from the mean. Small sigma, very packed toward the mean. Larger sigma spread out. Also notice that the height of the curve is changing there in the middle. For one thing, when you plug in the mean, this exponent becomes 0, and this e to the 0 is 1. So what you get is 1 over sigma times the square root of 2 pi. Well, the bigger you let s be, the smaller that fraction becomes, which means you have a smaller height right there at the mode, which of course the mode and the mean, the median are all the same thing. Now, of course, think about this. This makes sense because the total area under the curve is what? Yep, it's got to be 1, right? So the total area is 1. And so to keep the area of the 1, when you bring this in, you have to actually, it's going to force that to be higher but tighter packed, and then higher and narrower in the middle. And whereas if the sigma is bigger, it's shorter and fatter as you go way out here. So there is an example of some different changes in what happens to the normal distribution as we change the standard deviation. And it really doesn't matter what the mean is. If we move that around, the mean could be negative even, but the standard deviation has to be positive. So here's some graphed in Graphmatica. So changing sigma alters the spread, and we've seen that sigma really is the standard deviation. A lower standard deviation means less spread, more area near the mean, and it'll also be a little taller in the middle because the total area stays 1. Whereas a higher standard deviation means more spread, the area is spread out further away from the mean. In these examples here, I always let the mean be 0. Okay, so it's going to be by this formula. I've replaced the mean by 0 and simplified. But I'm putting various values for sigma. In fact, I chose 1/2, 1, 2, 3, 4, and 5. And so 1/2 is the narrowest and tallest right here, this yellow one. The red one is the standard normal, where the standard deviation is 1. Standard deviation 2 is this one here. Standard deviation 2 is the aqua one. Standard deviation 3 is the purple, and then so forth, 4 and 5. So notice the bigger the standard deviation, the shorter and fatter, the more spread out it is. Okay, let's look at one more thing. On the curve here, if you go one standard deviation out from the mean, to the left or to the right, you get to the inflection point. Now remember, an inflection point, or point of inflection, is a place where it changes from concave down to concave up. So here we are going out 1, 2, 3, and 4 standard deviations. So right here, this point, and this point, let's make them really big for just a moment. Those points right there are the inflection points. So notice over here, the graph is increasing concave up like a right side up bowl. Then it goes to increasing but concave down. When it hits the mean, it's still concave down but decreasing. Hits that inflection point, now it's still decreasing but concave up. So notice it's concave up on the left and on the right, but in the middle it's concave down. And where it changes is exactly one standard deviation out from the mean. It's mu plus sigma and mu minus sigma. Okay, I think that gives us a pretty good idea of what happens when we change the mean and the standard deviation of the graph. We also got a good look at what happens of how that area is distributed there. Okay, and it doesn't matter whether it's a standard normal or not standard normal. Between the mean and one standard deviation above, you've got 34%. Similarly over here, even if this is shifted over a bit, okay, then still between the mean here, between the mean and this one standard deviation over in the curve and the axis right here, so this area right here is 34%. Likewise 34 here, so a total of 68%. Then you pick up a little more, but not as much, by going out another standard deviation to 95% and then 99.7% coming out. Might be useful just to kind of memorize those kind of landmarks. 68%, 95%, 99.7%. Okay, I think that gives us a pretty good idea of the basic characteristics of the normal distribution. And in the next video, we're going to look at some ways of calculating some areas with this and some shortcuts that are built in our calculator. It'll be pretty nice. See you next time.